Okay, so let's see, I'm in the wrong page. So here's what we were talking about last time. We're talking about vector surface integrals, so otherwise known as flux. So flux is the sort of the physical motivation for this new mathematical construction we're making. I'm going to go really quickly through the idea of how we come by this new construction. The reminder is we're looking at the flow of a fluid, right? So we're thinking of our vector field represents a fluid flow. Can't emphasize that enough. Don't think in terms of forces at this time. We'll come to that later. But anyway, for the moment, F represents the flow of a fluid. And given that the fluid is flowing, as it is, looking at a piece of surface, reasonable question to ask would be how much of, quantity per unit time of this fluid is actually flowing through that surface. Right? So the vector field itself is telling you the direction the fluid is going. It's telling you maybe the velocity that the fluid is flowing with. And that's just not the same thing as quantity, cubic meters of fluid per unit time that's flowing through this actual surface oriented the way this surface is. So anyway, we went through the motivation last time, and here's the idea. F dot n times the area. Pretty easy to motivate as how much fluid is flowing through this surface, and this is what we call flux. And we use the capital Greek letter phi. I guess I forgot to mention that last time. That's a capital phi. We use capital to avoid confusion with the lowercase phi that we use for spherical coordinates. Okay. All right. So what if it's not a flat piece of surface? Well, chop it up, add it up. Right? So on each little piece, it's approximately flat. And the vector field is approximately constant. And so we can do a good job of approximating the flux. If we can do that on each little piece, then over the entire surface, you just add up all those little approximations. That should, fingers crossed, give you the total flux. And generally it does. You have to, there's conditions on regularity and stuff, but we're not going to worry about that in this class. Okay, how do we actually get our hands on this kind of an integral? How do we do it? Right? Well, so as usual, we have a domain that we don't like. How do we deal with domains that we don't like? We find ways to view them as images of domains that we do like. And of course, we love rectangles, but the more important feature of this new domain on the left is that it's dimensionally familiar, right? It's a two-dimensional thing in a two-dimensional context, and we know how to do double integrals. So that gets rid of the dimensional awkwardness of this two-dimensional surface in a three-dimensional context. How do you deal with that? Okay. So we've already done pullbacks of surfaces through parameterizations, right? For a different purpose, right? Where we were computing scalar quantities like mass, right? But nevertheless, we already have this development, most of this development here, and the only new thing we're introducing is the idea of this ds vector here. And the way I like to think about this ds vector is that it is a single mathematical object that tells you everything that you could want to know about the little piece of surface that it's representing. So its magnitude tells you the area of the piece of surface, right? And the direction that it points is telling you, by perpendicularity, telling you how that piece of surface is oriented, right? So if you know the direction that the normal vector is pointing, well then you know how that piece of surface is sort of sitting in space. Okay. All right. And so piecing all this together, this is about where we ended last time. If you want to add up a bunch of little pieces of flux, keeping in mind that each little piece of flux is computed by that formula, right? Well, formulas on the previous page allow us to rewrite nds as ds vector or capital N du dv. Right? And so we've got three different ways to represent this process, one of which is highly computationally convenient. This, you'll notice, everything in this formula is in terms of u and v. Everything's in terms of the parameterization. That's a double integral in the UV plane. We can totally compute that one. Okay, do keep in mind the merits of these other forms, though, and we talked about this last time, so I'll be quick. This one is the one that most directly connects to the physical motivation for writing this thing down in the first place. So that's a very reasonable notation to use. The book uses that notation mostly, and that's fine. I like this notation here the best. If nothing else, it's the shortest one. It's the easiest one to write down, just in terms of finger effort, right? But also, I'm a big fan of the idea that this point of view, thinking of the ds vector as being the all-inclusive, everything you could possibly want to know of that piece of the domain. That notation's really very elegant, right? You've got a dot product, sure. On one side of the dot product is what I might call the integrand, the thing that's independent of the surface. And on the other side of the dot product is the part of this expression that directly relates to that little piece of surface. So it's very organized. It's very natural, really, in my opinion. Anyway, that's the way I think about it. Okay. All right. Okay, so this is where we ended last time. So we're almost ready to do a calculation. The calculation, of course, is going to just be a plug and chug off of this. But we've got to worry about setup and that kind of thing. But there is one warning that I want to give you before we go on to the calculation, and that is about orientations. So before I get to the warning, I want to do a flashback to something that was it's not something we had to worry about. It was something that was perfectly obvious back when we were doing vector line integrals. Anyway, let me just quit foreshadowing. Let's just do it. Let's see here. I'll come up to some space up here. So when we were doing line integrals, here's a curve. And if you want to compute the amount of work or something like that, some vector line integral on this curve, the obvious question you have to ask is the amount of work that it takes to move along this curve, which direction, right? If you want to know, maybe your line integral is computing, the amount of work. Well, sliding a heavy box up a steep driveway is a lot more work than sliding that heavy box down the steep driveway, right? Is kind of let go of it and let it go, right? Or put it into your hybrid car and put your foot on the electronic brake and charge your battery by virtue of the forces that the heavy box is pushing your car along with. Okay, so which direction you're going matters. All right, so of course it does. That's highly relatable. So are we going this way? Or are we going this way? Right? Everybody on board? Okay. Well, how do we sort of, indicate which of those we're doing? Well, we do it with how we parameterize the curve. And this is why I say this wasn't a mystery when we were doing with this. When you parameterize a curve, there is sort of obviously a direction in which you're parameterizing it. Because if this curve is, a function of time, and you've got an interval over here, A to B, well, you can ensure that you parameterize it that way by having this, let's call that parameterization x, have this be x of A, and as time increases, just make sure you're actually going the direction you want to be going. Right? There's really no challenge in deciphering which way you've done it. And then, of course, this endpoint here is x of B. All right. So the point is, the parameterization dictates the orientation that you're implicitly imposing on the question when you're computing that, work calculation or whatever it is that you're computing. Okay. The parameterization imposes an orientation. So if the question asks you how much work does it take to travel in the indicated direction on a curve, when you parameterize, you guys all, of course, have to go to the trouble of thinking through, wait a minute, am I parameterizing this the right way? And if you parameterize it the wrong way, you're going to get the wrong answer. Right? I mean, it's perfectly clear. Everybody happy with that? Okay, so what's the big mystery? Why is this worth discussion? Well, the weird thing is that the same thing happens with surfaces, and we've never really thought about it before. But it's entirely analogous. When you parameterize a surface, I'll draw a picture here, some some surface. And parameterization might be something like this. You maybe some rectangle here, and there's your, x function of u and v. Right? That parameterization has coded into it an orientation on this surface. I mean, I never really thought about it that way. But partly, I get it. Maybe it's because, we don't see u and v as being time. We're highly invested in this idea of when you parameterize the function of t, then t is time. And we have really internalized this idea of time goes a certain direction, right? It's really relatable, right? So, and u and v are just numbers. Right? So we don't think of them as being oriented things. So how does this parameterization give you an orientation? Well, keep in mind the formula for n is xu cross xv. Translation, the parameterization dictates your capital N. And, of course, your capital N is going to then, in effect, dictate an orientation for you. Right, this is totally analogous to in the curve scenario. It's totally analogous to. I didn't mean to do that. Your parameterization dictates your velocity by way of a computation derivative, right? And then your velocity tells you your unit tangent vector. Right, so there's this and this are analogous. Okay, so punch line up here. Again, it's just extremely obvious that if a curve is given to you with an orientation, well, don't parameterize it backwards, of course, right? I mean, what could be more obvious? Make sure you parameterize it the way they told you to parameterize it, for crying out loud, right? And of course, you could parameterize it backwards, and that would be silly, right? So, same thing here. Give me 2 seconds. With a surface, if you were given an oriented surface, this, here's a surface. This thing oriented, let's say that way. If the surface is given as oriented, when you parameterize that surface, don't parameterize it the wrong way. Which is worrisome because it's not clear how your parameter. How do you anticipate, other than just doing this calculation, how do you anticipate whether you are parameterizing it the right way or not? Right? Nevertheless, it remains. This is a problem we have to worry about, and there's a great answer to the question that I'll get to in just a moment. Yeah, go ahead.
So for the line integral, are you parameterizing it based on the endpoints? Is that the direction?
Yeah, well, I mean, so when the curve is given, right? This curve here, when this is given as a curve, they'll usually say, oh, it's this curve, oriented, let's say to the right, or however they might phrase it, right? So that's how the parameterization will be given. Now, what parameterization are you going to stick onto it by your choices? That comes from the velocity vector, right? So you write down your parameterization. When you write down this, right, there is then correspondingly a velocity vector of your parameterization, and that velocity vector then gives you your t, your unit tangent vector, which indicates orientation. Yeah. Does that make sense? Yeah. All right. So, heads up is all I'm going to say on this for the moment. Make sure you don't parameterize a surface, the wrong way. All right. Now, keeping that in mind, we're going to sort of pocket that point for the moment and go on with the calculation. Okay. So here's our situation. We want to compute a flux. We have a fluid flow. We have a surface. And given a fluid field and a surface, we can very reasonably ask, what's the flux? Right? And we've got formulas. We're going to plug and chug. Okay, and here we go. Vector field. Let's see here. Now, what do we do? Where's that capital N come from? Well, don't forget capital N comes from the parameterization. So I can't do anything with that capital N, or, in effect, this ds. I can't do anything with those until I parameterize. I'm going to parameterize. Notice that my surface is a graph. All right, surface is a graph. We know how to parameterize graphs. We're going to use the graph parameterization. All right, so we're viewing x and y as u and v. And then z is, well, you know, whatever it has to be. Z has to be that. If z is x squared plus y squared, and if x is u and y is v, then our hands are tied. That's what z has to be. Okay. All right, so great trick. Play the usual game, xu and xv. Here's the resulting capital N vector. Right? And here's where students make a mistake. This is where the mistake gets made. Lots of students at this point will just say, okay, well, look, the formula, it says right here, clear as a bell, F dot capital N, and plug and chug. And that would be a mistake. So this is where we go back to this orientation point. Right, so we have to worry about. I mean, we made up a parameterization. We kind of made it up. I mean, why did we choose the graph parameterization? Because it was easy. Right? That's not a justification. Right? There is no rule that says that when you take the easiest algebraic choice that it will be right. Right? If there's two different possibilities of ways that you can do this, this is a coin flip. Right? So we have to check and see, did we parameterize this thing right side up or upside down? And easy to tell if you go to the statement of the question. So again, here's my surface, and most of this discussion is talking about the specifics of what points are a part of my set. But then here the key language, oriented downward. Right, so this surface, there's two different ways that hypothetically one could orient this paraboloid. This paraboloid here, it could be oriented, you might say, let me use a different color. You might say, this would be a reasonable orientation, right? In other words, the normal vector is all pointing perpendicular to the surface. You might say inward, right? But another perfectly plausible orientation on this surface, another perfectly plausible choice of which direction does lowercase n point. Keep in mind, lowercase n just has to point perpendicular to the surface. It could point what you might call outward. Right? So when we parameterize, we have to be careful and make sure that we don't inadvertently parameterize the wrong way. We have to not inadvertently pick the wrong of these two choices. Now, again, the phrasing of the problem, it says right here, oriented downward. Downward between these two, between this green orientation and this blue orientation. The green one is the only one that has vectors pointing downward. Yeah? So the statement of the question is telling us that we need to parameterize it that way. So when we do our parameterization, the results of the parameterization have to be consistent with that downward orientation. And what did we do? Well, let's check it out. The result of our parameterization is that our capital N vector is that thing. Pay careful attention. Notice that this third coordinate is 1, which is positive, which means that it's inward. Upward, you might say. So we blew it. We parameterized this thing the wrong way. Everybody see that? Okay, so, oh gosh, do we have to start all over? Do we have to do a brand new parameterization and hope that one is right? Or how do we deal with this? I don't think that that's necessary. So here's the really good news. The good news is if you parameterize it backwards, just like with line integrals, if you parameterize it backwards, you're just going to get the exact negative of the right answer. So what I encourage us to do at this point is to just write down something like this, stick a minus sign on there as a result, and press on. It's fine. Right? I mean, think about it, if you were doing a line integral, if you were computing the amount of work that it takes to blah, 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 or the amount of altitude change between 2 points, and you think, whoopsie, I measured the altitude change from here to here. Oh, the question wanted me to go from there back to here. Did it back? Well, then you got the negative of the answer. So just stick a negative on and it's fine. Same thing here. Does everybody see the solution? So it's very important to see what the problem is and how sneaky, how hidden it's so easy to not see how you've inadvertently parameterized this surface, right? So heads up, right? And then you have to look at what you've done and sanity check and see if it's right or wrong. If it's wrong, you're off by a minus sign. Mea culpa. Put your minus sign in there and go ahead. Yeah, it's fine. Yeah.
For a problem, will you always just tell us the orientation of it?
If the question asks you for a flux, then flux is not a well-defined thing unless you say in which direction through the surface. Yeah. So there's somehow or another, and it may be kind of implicit in the phrasing of the question in some way or whatever, right? But there needs to be a choice in the statement of the question somehow or another as to which way is the right direction through the surface. And so you got to be paying attention and looking for that, and then find it. Yeah, right. Mm-hmm. Yep.
So most of the time, is it going to be just looking at the z coordinate of?
So that's a great question. Let me talk about that a little bit. It's not always this or always that. It's different in different cases. So by the way, let me talk a little bit about language. I'm going to totally get to your question. 2 seconds. So again, we have these two different choices of orientations. We have the kind of this one. And then we have the other one. And the problem in talking about these orientations is that each one of these orientations, let's say the blue orientation there, that blue orientation is not a single vector. It's a whole bunch of vectors. It's infinitely many vectors associated to infinitely many points on this surface. Right? Wow. Okay, so I can't say, the orientation that points and then give a single direction, because they point all sorts of different directions. Right? It's a nasty little problem. So what we tend to do is we tend to look at all of them together and ask, what is it that distinguishes those vectors from these vectors? Right, and there's different choices that you can make, and it depends on the situation that you're looking at. Here, I could very easily say, for example, that notice that all those blue vectors point at least somewhat up, and none of the green vectors point in any sense up. Right, so if I say upward versus downward, that makes the distinction, and of course it's not perfect. None of those blue vectors are pointing exactly up. Well, hardly any. There's one of them, right? But mostly they're not pointing exactly up. But it makes a distinction. It's not always going to be like that. It will be, for example, suppose that our surface is a sphere. Well, then our two orientations are like this and like this. Neither of these collections of vectors is distinguished by the word upward. Right? Some of those green vectors are pointing upward. Some of those blue vectors are pointing upward. If you say oriented upward, that makes no sense in this context. Everybody see what I'm talking about? So what is it what's the distinguishing, how do I tell apart, these blue vectors are all, and the green vectors are, how do you finish that sentence? Right? And so what I would say here is the green vectors are pointing inward. Right? The blue vectors are pointing outward. Right? So, context is going to make a tremendous amount of difference, and you have to think about, given how the question is phrased, or given how you're describing whatever your surface is, you have to come up with an interpretation that makes sense appropriate to that surface. Give me 2 seconds. So your question was, how do you tell? Right? So how would I mathematically tell if I had some formula for normal vectors? In this case, where we were talking about the paraboloid, upward is easy to distinguish. You look at a z-coordinate, right? In this case over here, that doesn't work, right? So you'd have to do something different. You'd have to figure out how to tell, is a vector pointing away from the origin, or is a vector pointing toward the origin? right? And so, one thing you could do, for example, is take your formula, plug in the North Pole, right? And just look at that specific one. And if it's pointing upward, then you've got the blue orientation. And if it's pointing downward, then you've got the green orientation. Does that make sense?
Well, if you plug in one point, how do you know that point is at the bottom of the sphere? So
well, you gotta know your surface well enough to know what point you're plugging in, right? So you have to be able to, I'm not going to be able to reduce this down to plug into the following form. The formula will dictate for you, right? You're going to have to look and interpret and make sense out of it and interpret in that context. Yeah, that's the nature of the beast. Yeah, you had a question. I'm sorry.
Yeah. So for the surface that we're working with, we can attribute downward to being a negative, z.
A negative third coordinate. That's right. Yep.
For the sphere.
Yeah.
Does the inward
Well, we got to think about it, right? So I mean, it's not all of these green vectors here have different z coordinates, right? Some are plus, some are minus. So that's not going to distinguish. So I was telling her is that you have to. In this case, I think a reasonable way to do it, anyway, would be to pick a single point about which you do know what's going on. Right at the North Pole of this sphere, I know which way. Outward is up when you're at the North Pole, right? Downward is in when you're at the North Pole, and then you can just look at the z coordinate for that point.
Okay.
Yeah, right. Okay, so heads up on that subtlety. The rest of this question is very plug and chug. We computed in on the previous page. The vector field was given. Okay, well, let's see here. Wait a second. The vector field was x, y, -1, but don't forget x and y are u and v, right? So the vector field becomes that. And plug and chug. And this integral right here, polar coordinates, is going to be very handy in computing that integral. And off you go. Yes?
So in order to get this as a negative from the beginning, what would we just have to have completed a negative?
Say it one more time. I'm sorry?
In order to get the z coordinate to be negative from the beginning.
Oh, you're wondering how would you parameterize the correct way from the start? That's a great question. When you have a graph, and especially in a situation like this, it's just really, really highly desirable to use the graph parameterization because it's always the same, and it's very nice, right? So I would suggest that we reevaluate the importance of your question of maybe it's just not that hard let's just throw in a minus sign if necessary. Right. Okay. Now, if you really do want to, right? Let me say it differently. There's nothing somehow more meritorious about getting it right in the first place. Okay. It is perfectly fine to parameterize the most convenient way to then recognize whoopsie backwards minus sign. Right. That is perfectly legitimate, no problem at all. But if you really want to, if you switch these. If you just switch the x and the y, then that'll make it go backwards. Yeah, right. Yeah, right. But it doesn't matter. Yeah. Okay. Here's another example. Now, so the last one we did was the very pluggy chuggy one. This one's going to be a little bit clever. So here we're going to compute it's another flux, right? Computing the flux. We have a vector field given. Yikes. We have a surface given, and off we go. Now you could plug and chug, I suppose, but let's try to anticipate and see if we can get lucky here. Notice this surface is the part of that plane that satisfies a certain inequality. So our surface, is it's got some weird shape described by this quartic inequality, but it's sitting inside of this plane, which means every point in that surface has y equal to 3. And that's a big observation. So let me zoom out one notch here. So this y is equal to 3. Right? Boom. Score. So all of a sudden, our vector field simplifies very nicely. All of this ugliness becomes that. And we have a 0 in there. Everybody's happy with that part first? Okay, now again, you could parameterize and go through the whole process, but do notice another thing here. Because we're in this plane, that means that our normal vector is easy to write down. Right, our ds vector. The plane is perpendicular to the y-axis. That means the normal vector is parallel to the y-axis, which means it has no x component, it has no z component. Those are both 0. So there's still a fair amount of ugliness left in this equation, but all the ugliness cancels with our zeros. So the answer is 0. Everybody happy? Okay, so I'm a big believer, don't put on the blinders and take a deep breath and plow forward until you've kind of looked around, look for your potential for good fortune. What is it that's geometrically convenient about this, and how can I use that to my advantage, right? Etc. And so, try to consider all avenues before you decide to brute force it. Okay. This is the last. But yeah. Okay. All right. Fine. I need to move along. I want to point out a strong analogy between vector line integrals and vector surface integrals. And this is not a coincidence. This will kind of look like a coincidence at first, right? But this is very much not a coincidence. So I mentioned mostly for cultural purposes. It's good to know that both of these things, vector line integrals and vector surface integrals, very different in terms of how we motivated them, right? Vector line integrals by work, vector surface integrals by fluid flux, right? Seemingly very different physical objects, but they are both special cases of this other thing called differential forms, integrals of differential forms. And this is deep water, and we can't go into it in Math 212. It's just, we couldn't begin. There's nowhere near enough time to do this. But I think it's valuable to know that even though they look different, even though the physical applications, physical motivations are different, they are in fact kind of the same thing in different contexts. So a vector line integral in space is really just an integral of a certain kind of a differential form. And a vector surface integral, a flux through a surface in space, it's just a different kind of a differential form. Right? So knowing that these are both special cases of kind of the same thing makes it not particularly surprising that they have a lot in common. There's a lot of analogies, so I want to point out some of these analogies here. And by the way, I think there's another reason that's good to know about these analogies, and that is what you understand about one side will help you understand the other side. So, okay, anyway, here we go. Now I've drawn, here's a parameterization of a curve. Why did I draw it sort of top to bottom instead of left to right? It's because my paper is only so wide, right? This is strictly a typesetting, a page layout thing. So pardon the weirdness of parameterizing sort of downward instead of sideways, but whatever. So we have a parameterization of a curve, and here's a parameterization of a surface, right? As usual, I'm drawing just, the sort of little pieces. So we've got, by way of this parameterization, a velocity vector. From that, I compute the unit tangent vector, and then by the magnitude of the velocity vector, etc., I can talk about this ds quantity, this length. Oh gosh, let's see, what am I going to, colors. I'll use dark blue, okay. So ds is the size of that little piece, and all of that is encapsulated in this one thing, our dx vector. Okay, so here's the analogy. Notice that with the surface integral, right, in the same way that the parameterization gives me a velocity vector over here, my parameterization gives me this capital N vector, xu cross xv. It comes directly from the parameterization. That gives me my unit normal vector that describes the orientation, just like the unit tangent vector describes the orientation on the curve, playing analogous roles, right? The magnitude of capital N helps me to compute ds, the size of this little piece of surface, just analogous to looking at the size of a little piece of curve, right? And sort of combining it all together, we came up with this ds vector. That sort of tells you everything you want to know about that piece of surface, just like the dx vector tells you everything you'd want to know about that piece of curve. The analogy is really very strong. And it persists even in the formulas down here. So notice, now here's a bunch of formulas that we established for vector line integrals a long time ago. That's all old news, right? Likewise, over here, a bunch of formulas that we've developed over the last few days. A bunch of formulas involving the participants in a vector surface integral. And notice the structural layout is really the same everywhere. Let's see here. I'm just trying to make sure I'm being consistent with my color choices here. Right? I mean, it's just the analogy is really pretty strong here. Not a coincidence. They behave in very strongly analogous ways because they're special cases of the same thing. Again, in ways that we sadly can't talk about in this course. So anyway, be aware, heads up. You'll notice again also that there's a bunch of analogies in how we write these things down. There's, my favorite notation for each of these. Then there's the one that comes directly from the parameterization. Then there's the one that directly notes the unit orientation. And then there's the one that talks about components of the vector field, which is, of course, just equivalent to indicating, which part of the vector field we're interested in each case. Very strong analogies. One of the differences, where the analogy kind of breaks down a little bit, is we sort of enter into the work integrals with that one. And then from that one, we motivate all the others. Just, our physical motivation sort of starts there. Whereas with Flux, we enter into it with this one, and then that motivates these others. So, our connection to our application's a little bit different. All that does is conceal the analogy. That doesn't break down the analogy. Okay, all right. So how you can make use of this. If you find yourself having trouble making sense out of, what is the deal with I don't get this ds vector that Bray is always talking about. What is the deal with the ds vector? Oh, just realize that it's playing a role very much like the dx vector did in vector line integrals. Right? So use what you understand about this to help you understand more about that, and etc. Okay. Alrighty. Right. So that's something we were talking about earlier. The parameterization gives rise to the velocity vector, which gives rise to your orientation. Right? And then which will, of course, obviously, don't parameterize backwards, right? But now we can see right here in this diagram, well, then likewise, right, when you're parameterizing a surface, that gives rise to your capital N vector, which by analogy gives rise to your orientation on the surface. Same thing. Okay. All right. All right, so I want to talk a little bit now about coordinate surface integrals. Y'all may recall we spent a little bit of time on this notation way back when was it? It was a week or two ago. We were talking about vector line integrals, and of course long ago we established dx is v dt, right? Boring. V is x prime, y prime, z prime. Well, of course it is. And so then we found ourselves looking at this expression, and then we, having never really done so before, asked, well, what should we call that thing? And it seems pretty reasonable to call it dx. I mean, what else are we going to call it? It's perfectly natural, right? And then I did a little bit of foreshadowing, and I described it as such at the time that, how do you view dx? You can view dx as relates to a projection. So think about, for a given piece of curve, think about if you were to project that piece of curve down to the x-axis. Seems weird, but let's pretend. Right? You project that piece of curve down there, and you look at how big is that projection, and then you ask what direction. Right? When you look at the direction on the curve here, that direction on the curve suggests a corresponding direction. And are you going the same direction as the x-axis, or are you going the opposite direction? Right? So like I say, seems like a weird point of view to take on this dx. Why not just view it as how much did x change? Okay? But nevertheless, same. This is really effectively the same thing. So again, let's think about this new point of view on dx is that you were looking at a projection of that piece of surface down to the x-axis and thinking about the nature of that projection. Okay. All right. So here's why we care about that. Very similar thing you can do with surface integrals. Okay. Now I'm going to try to do this as analogously as I can. Old news, not about dx, but about ds. Right? That's the analogous thing. Sure, V is computed by that formula. Well, likewise, N is computed by that formula. And again, you can stretch that out into coordinates, right? X prime, Y prime, Z prime. We can write that out with, Leibniz notation. Well, analogously, let's stretch that out into Leibniz notation. By the way, this is a calculation that everyone should do at least once. It's no big deal. It'll take you about a minute, right? But if you just write down exactly what these are, XU is, XU, YU, ZU, etc., XV. Likewise, write down the coordinates. Crank out that cross product. Notice that what you'll find is that each one of the coordinates is a little determinant. And those determinants we already have an existing notation for, and they're those things right there. So now that's going to take you a minute or two, right? It's just a matter of writing down the cross product formula, though. But this is what XU cross XV gives you. So take a couple of minutes, convince yourself that that's true. Okay, so up here we found ourselves looking at that and just could not stop ourselves from calling it dx. It was just borderline obvious. Of course we're going to call it dx. What else would we call it? It couldn't be more clear that that's what it should be called. Not so here. What should we call that? What is that? Right? And so this is where we need to sort of do a little bit of thinking. So here's the clever idea. It turns out there is a really natural way to think about this. And I'm going to look at this one here in particular just because it's a little easier to draw the picture. But let's think about how this relates to this projection here. And I'll bet you I can do that. There we go. Okay. This expression, partial xy, partial uv, makes us think about change of variables. Right? Somehow or another we need to view x and y as being functions of u and v. But that's not what we have. We don't in our parameterization, we don't have just x and y as functions of u and v. We have x, y, and z all as functions of u and v. I didn't circle that very well, did I? So if I want to understand partial xy, partial uv from this, what I've got to do is figure out how can I sort of get rid of that z coordinate. How can I I just want to lose the z, just forget the z. And different ways you can think about that. The most natural way to think about that is let's just project down to the xy plane, right? And then now, of course, that's morally, you're just going to lose the z coordinate, and the x and y you keep, and now you have a point in the xy plane. And so now we have then a function. X and y are functions of u and v. Right? This thing, I can give a great interpretation of this, what I have circled here in green. That thing is what I get when I take du dv, right? And I multiply by, whatever that stretching factor is. The stretching factor that gives how x and y are stretched out as functions of u and v. It's this area. There. Namely, it's this area here. It's the area of the projection of that piece of surface. Everybody happy with that? Well, thus the analogy. This thing down here is the size of the projection of that piece of curve, right? And this thing here, that coordinate of our ds vector is the size of this projection of our piece of surface. Okay. All right. It's absolute value. Sorry, of course, the absolute value is what we're talking about. The absolute value is what makes it a stretching factor, and thus allows us to interpret it as area. Next question about the plus and the minus. What happens if this is negative? What does that mean? This is actually a really easy question. If that thing is negative, well, keep in mind what it is it's the third coordinate of our normal vector. Right? So if this thing is positive, all that means is that this vector is pointing up ish. And if this thing is negative, I think I said that backwards. If this thing is positive, that means that this vector is pointing up. And here, let me color code this. Is pointing up. If this thing here is negative, all that means is that this vector here is pointing down. Yeah? Okay, well, so how does that relate to projection? Well, I appeal to your geometric intuition. If you have a surface here whose normal vector is pointing up, then when you project it down, it's projecting what I'm going to call right side up. Right? Whereas if the thing is down, if this surface is oriented downward, then when you project down like that little piece of surface, it's like it's pushing down into the plane upside down. You might say backwards. Though certainly the wrong way in whatever, we had this idea of the XY plane pointing up and this thing's pointing down. That's sort of the opposite of the way that it's kind of supposed to. Okay, so just like this, the sign, whether that thing is positive or negative, just tells you whether you're projecting into the plane upside down or right side up. Okay. All right. So nice punchline then. This thing here. Oh, wrong color. This thing here. Partial xy, partial uv, du dv. That thing represents a piece of area in the xy plane, along with a plus or a minus appropriate to whether we're talking about a right side up projection or an upside down projection. So dx dy is a very reasonable thing to call it. It is a piece of the xy plane, and there is this associated orientation of, is it projecting in there right side up or upside down? So dx dy, very natural. Okay. You guys, on your own, can do analogous arguments for why this should be called dy dz and this should be called dz dx. And y'all can think that through You do have to be careful, by the way, with calling this dz dx and not dx dz. Otherwise, you'll notice that this determinant, if you switch the columns, you're going to get the negative of the value of the determinant. So it really has to be partial z comma x. And as a sort of acknowledgement of that, we write dz dx, not dx dz. It's not the same. Right? And now just a little bit of algebra. There's really not that much left to do here. But having agreed to call that, and likewise here and likewise there, remember this whole discussion was about understanding our ds vector better. Well, if our ds vector is dy dz dz dx dx dy, then we have a notational alternative for flux. Flux can be written like that. And y'all may recall there was a equivalently awkward notation for vector line integrals way back when, right? Which, I told you about because some people like to use that notation, so be prepared for it. Right? Same deal here. Some people like to write flux like this. And there is a fantastic, deep, sophisticated mathematical basis motivating why you'd want to do this. It's called differential forms. And again, we can't talk about that in this context. So it's not that this is a bad idea. It's a great idea. Outside of the context of Math 212. Right? So be prepared. You're going to see this. And when you do see this notation, just remember that all they mean by that is that this is your vector field F. Okay. All right. See y'all later. Have a good day.